A magnitude 6.4 earthquake tore through the floor of the Bismarck Sea on July 13th, and it caused no damage, no casualties, and no tsunami. So why can't scientists stop watching the water around it? Because that earthquake struck barely 85 kilometers from a volcano no one can see, a hidden ridge that erupted for 5 straight weeks this year, and then, just days ago, appeared to fall asleep. Now, a strong, shallow rupture has shaken the ground right beside it. The shaking is over. The real danger is what the ocean does next. And the first sign of it, if it comes, will not be a warning siren. It will be a color, changing on a satellite image. If a hidden volcano that can move the ocean is your kind of story, subscribe so you don't miss the moment this one shifts. Comment with how close you live to a fault or a coast. Let's get into it. Something struck the floor of the Pacific on July 13th, 2026. And the most unsettling part of it is not how hard it hit. It is when it hit. At 8:53 in the morning, Coordinated Universal Time, the United States Geological Survey recorded a magnitude 6.4 earthquake in the Bismarck Sea, north of the island of New Guinea. The rupture was shallow, only about 10 kilometers down, roughly 6.2 miles beneath the seabed. Around 64,000 people felt a light shaking. Another 22,000 felt something weaker, a faint sway. There were no reports of damage, no collapsed buildings, no casualties, no sirens. The Pacific Tsunami Warning Center looked at the numbers and said what everyone wanted to hear. No tsunami threat from this earthquake. Pause for a second on how those numbers came together, because in the first minutes after a large quake, the picture is always a little blurry. Different monitoring agencies around the world reported the size slightly differently at first. Early automatic solutions landed somewhere between magnitude 6.3 and magnitude 6.5 before the United States Geological Survey settled on 6.4. That spread is completely normal. It reflects how fast the first estimates are generated and how they get refined as more seismic stations report in from around the planet. The depth firmed up at around 10 kilometers, and that shallow number is not a technicality. It is one of the most important figures in this entire story, and I will keep coming back to it. The location sharpened too. The epicenter sat roughly 192 kilometers, about 120 miles, southeast of Lorengau, the small provincial capital on Manus Island. It was around 263 kilometers west-southwest of Kavieng, and about 315 kilometers northwest of Kimbe. It was well offshore, out in the open Bismarck Sea, far enough from any sizable town that the shaking arrived as a gentle sway rather than a violent jolt. That is why the human impact was so light, and why almost no one outside this corner of the Pacific even registered that it happened. Put the size of it into perspective against the quakes that came before, because this was not just one more tremor in a busy year. A magnitude 6.4 does not sound dramatically larger than a magnitude 5.4. It is only one number higher. But the scale that measures earthquakes is not a normal counting scale. It is logarithmic, which means each step up represents a large jump in the actual energy released. A magnitude 6.4 unleashes something like 30 times more energy than a magnitude 5.4, and roughly 11 times more than a magnitude 5.7. So when I tell you this was the strongest event to strike this patch of seafloor all year, I do not mean it edged out the others. I mean it towered over them, and under almost any other circumstances, that would be the end of the story. A strong quake in a remote stretch of ocean, felt by a few thousand people, causing no harm, generating no wave. You would never hear about it again. But this earthquake did not happen in an empty part of the sea. It happened right next to something. Something we spent weeks watching earlier this year. Something that had just finally gone quiet. To understand why a harmless earthquake has scientists refreshing satellite feeds tonight, you have to know what is sitting 85 kilometers, about 53 miles, to the northwest of where the ground broke. There is a volcano down there. Not a mountain you can climb. Not a cone with a webcam pointed at its crater. It is a hidden volcanic ridge under the Bismarck Sea, and earlier this year it woke up for the first time in more than half a century and erupted, continuously for over a month. Then, just a few weeks ago, it seemed to fall asleep again. The eruption faded. The official report said activity had dropped to very low levels. The sea went calm, and a lot of people, myself included, let out a breath. Now, a magnitude 6.4 earthquake has hit the crust right beside it. And here's the thing I need you to hold on to for the next hour, because everything else hangs on it. The danger here is not the shaking that already happened. The shakings is over. The danger is what the ocean does next. Let me be precise about what we do and do not know, because this is a story where the difference matters enormously. We do not know that this volcano is erupting again. It almost certainly is not, at least not violently, not in a way that is making headlines. What we know is narrower and, honestly, stranger. A strong tectonic rupture just shook the ground next to a submarine volcano that we cannot fully see, cannot fully map, and do not fully understand. The volcano did not cause the earthquake. I want to be very clear about that from the start. But the earthquake struck close enough to that volcano that the next round of satellite images and underwater sound recordings suddenly become some of the most interesting data on Earth, because the volcano only looked calm at the surface. The eruption may have dropped below what our instruments can detect. The pumice may have dispersed. The plume of steam may have thinned to nothing. But the fault system underneath it did not go anywhere. The magma-heated environment down there did not cool overnight. All of that was still sitting there, quietly, when a magnitude 6.4 rupture arrived and shook the entire neighborhood. So the question that opens this whole investigation is not whether you felt this earthquake. You almost certainly did not. The question is whether a sleeping volcano felt it. And to answer that, we have to go down to a place on the map that, until a few months ago, almost no one on Earth had ever heard of. Here is what makes this particular volcano so dangerous. You cannot see it. It does not rise out of the water. It has no crater you can stand at the edge of, no lava you can film, no summit that pokes above the waves. It is a ridge on the ocean floor, and the water above it is so poorly surveyed that scientists still do not know the exact shape of the structure that was erupting down there. Think about that for a moment. In an age when we can photograph the surface of Mars and map the far side of the moon, there is a currently active volcano beneath the sea, north of Papua New Guinea, whose true form is a genuine question mark. We call it Titan Ridge now, but that name is only a few months old. For most of us, it did not exist until this year. It was pieced together from old records of submarine activity in this region, especially some eruption signals detected back in 1972. That is the only prior episode anyone knew about, and even then, no one saw it. It was heard, picked up as sound traveling through the ocean, not observed with eyes or cameras. Then, for 54 years, silence. That word heard deserves a moment, because it is central to how we know anything about this place at all. Sound travels remarkably well through seawater, far better than it travels through air, and certain low frequencies can carry across entire ocean basins. Networks of underwater microphones, originally built for very different purposes, pick up the rumble of undersea eruptions and earthquakes from thousands of kilometers away. So when 1972 came and went with signals but no sighting, that was not a failure of attention. It was simply the only way this ridge could be detected. Nobody had eyes down there. The ocean spoke, and the instruments listened. That same blindness shapes what we know today. Even during this year's eruption, when satellites were watching the surface closely, the actual depth of the vent was uncertain, with estimates ranging from a few hundred meters below the surface to well over a kilometer down, depending on which method you trusted. Consider what that means. We could not even agree on how far down the mouth of the erupting volcano was, to within several hundred meters. The earthquake catalog for this region has a flaw as well. The local instruments can only reliably detect events down to around magnitude 4.5. Anything smaller slips through unrecorded, so every quake we counted during the eruption was only the top of a much larger unseen swarm rumbling beneath the threshold. When you hear that no volcanic earthquakes have been detected for over a month, hold it against that limit. It means no large ones. It does not, and cannot, mean none at all. What broke that silence this year was not a person looking into a crater. It was a satellite noticing that the sea had changed color. That is the detail I keep coming back to, because it tells you everything about how blind we are to this place. The eruption became obvious when spacecraft in orbit started seeing strange things on the ocean surface. Discolored water, a greenish stain spreading outward across the blue. Steam and gas rising from open sea where there should only be waves. Heat signatures blooming in the infrared. Warmth appearing in a place that should have been nothing but cold water. And then there was the pumice. When this volcano erupts, it produces these little grayish, sandy-colored volcanic stones, light enough to float. They gather into rafts, whole carpets of floating rock, and they drift with the currents until they wash up on shore. If you have never thought about floating rock as a hazard, consider this. What volcanic ash is to an airplane, pumice is to a boat. A raft of it can clog an engine intake and choke it dead. It can blanket the surface of the sea for miles. So even in its quiet way, this eruption was reaching out and touching the islands nearby. And it did touch them in concrete ways during the height of the eruption. Rafts of floating pumice drifted toward the Admiralty Islands and gathered thickly enough to interfere with boats and block stretches of sea access for the communities of Manus Province, the same province whose capital, Lorengau, felt this month's earthquake. For people who depend on the water to move between islands and to fish, a sea clogged with floating rock is not an abstraction. It is a road suddenly closed. Authorities in Papua New Guinea issued warnings about pumice, ash, unusual swells, and turbulent currents. There were even reports of the sea itself behaving strangely near the eruption, described by one fisherman as smoke rising off the water, with dead fish floating up as though the ocean had come to a boil. Satellites, meanwhile, watched a stain of discolored water spread across the surface and monitored the site for the possible birth of a brand new island, a temporary scrap of land that a submarine volcano can push above the waves and that the sea can just as quickly reclaim. All of that was the volcano awake. All of it faded as it went quiet. And all of it is on the table again, in principle, if this earthquake disturbed what lies beneath. This is the pattern recognition that matters. We did not find this volcano by watching the volcano. We found it by watching the water react to it. And that is exactly why the earthquake is such a problem. Because if this quake disturbed anything down there, we are not going to see the disturbance directly either. We're going to see the sea react to it, if it reacts at all. For weeks, the eruption escalated rather than faded. The plume climbed from around 9,000 feet early on to roughly 28,000 feet by the middle of May. That is not a minor puff. That is a column of ash and steam punching high into the sky from a vent hidden under the ocean. And then, after all that, it began to wind down. The activity weakened. The underwater sound signals declined. The pumice rafts started breaking apart. No volcanic earthquakes were detected for more than a month. The surface looked calmer. Everyone was relieved, because the great fear with a submarine volcano is that it builds a large, unstable cone that could one day collapse and shove a wall of water outward. That relief is what makes July 13th so jarring. The quiet phase had set in, and then it was interrupted, not by the volcano, but by a magnitude 6.4 earthquake tearing through the crust right beside it. To understand why that specific event, in that specific place, is so hard to dismiss, we need to look at what kind of ground this actually is. This is not a quiet ocean basin where nothing happens. I want to dismantle that assumption right now, because it is the assumption that makes people wave this earthquake away. The stretch of seafloor we are talking about sits at what I can only describe as a plate boundary puzzle, and the geometry of it is genuinely unusual. Remember those eruption signals from 1972? The ones that first told us something volcanic lived here? They came from the junction of two different plate boundary segments meeting in the same place. On one side, you have a transform fault system, where slabs of crust grind past each other sideways. On the other, you have what is called an oblique spreading zone, where the seafloor is being pulled apart, but at an angle rather than straight on. Put those two together in one location, and you get something that does not behave simply. The crust here is not just sliding. It is not just opening. It is not subducting cleanly either. It is being twisted. It is being stretched. It is being cut. And at the same time, it is being rebuilt. Now hold that image, because it leads directly to why the volcano and the earthquake cannot be neatly separated. In a place like this, where the crust is being pulled and sheared and torn all at once, earthquakes and magma end up sharing the same weak zones. The faults that slip in a quake and the fractures that let molten rock rise are, in many cases, the very same cracks in the very same stressed rock. So when a magnitude 6.4 rupture releases in this setting, it is not happening in some isolated compartment far from the volcanic plumbing. It is happening in the same fractured, twisting slab of crust that the volcano depends on. But let me be fair to the science, because this channel does not deal in fear without data. When the earthquake happened, the survey released what geologists call a moment tensor, and if you have ever seen one, you know it as the beach ball. It is that little circle split into colored and white segments, and it is not decoration. It encodes exactly how the rock moved, and this beach ball tells us something important. It does not look like a clean volcanic explosion signal. It does not look like a caldera collapsing. It shows fault motion, specifically what is called oblique strike slip with a normal component. Let me translate that, because the jargon hides a simple picture. Rock moved along a fault line, mostly with a sideways motion, and with some pulling apart mixed in. That's a tectonic earthquake. That's the ground itself breaking under stress, not magma detonating. And that fits this Bismarck Sea setting perfectly. The transform faulting and the oblique spreading written right into the way the rock slipped. Sit with what those two fault styles actually do, because their combination is the reason this junction is so productive. A transform fault is where two slabs of crust slide horizontally past one another, the way the more famous faults on land grind along for hundreds of miles. A spreading zone is the opposite kind of motion, where the crust pulls apart and new seafloor forms in the gap. Normally, you find these in separate places. Here they meet, and the spreading is oblique, coming in at an angle rather than head-on, so the rock is being sheared and stretched at the same time. That mixed motion is exactly what the beach ball recorded. Sideways slip with a component of pulling apart. The earthquake did not just fit the region in a vague way. It carried the region's fingerprint. There is a concept underneath all of this that makes the volcano impossible to ignore, called stress transfer. When a fault slips in one place, it does not release stress everywhere. It loads it somewhere else. The crust is like a tangled web, and pulling hard on one strand tightens others. a shallow magnitude 6.4 rupture reorganizes the forces across a wide area of surrounding rock. And because this quake was shallow, only 10 kilometers down, that reorganization happened close to the seafloor, in the same upper layer where a volcano's fractures live. A quake buried 40 or 50 kilometers down would bleed much of its influence into the crust before ever reaching the surface. This one did not have far to reach. It broke near the top, right where it could touch the plumbing. And this junction has a track record, which is the final reason to take it seriously. This is a corner of the planet where the crust is genuinely restless, where earthquakes and volcanism are not rare visitors, but permanent residents. The 1972 signals that first betrayed the volcano's existence came from right here, at this same meeting point of faults. The eruption this year came from here. The swarm of quakes that accompanied it came from here. And now a magnitude 6.4 has come from here. When that many independent events emerge from the same twisting seam of seafloor, the pattern is not a coincidence to be explained away. It is the signature of an active, complicated boundary doing what it does. So the idea that this earthquake is unrelated to the volcano, that it happened to strike right beside it by pure chance and means nothing, asks you to believe in a coincidence in a place that specializes in exactly this kind of overlap. So here's the revelation that anchors this whole first half, and it is not the one you might expect. The beach ball proves this was a tectonic quake and not a volcanic one. You would think that settles it, that it means the volcano is irrelevant. It means the opposite. Because being tectonic does not make this earthquake harmless to the volcano. It just means the quake was born from the same twisting crust the volcano lives inside. This does not prove that magma suddenly moved. It does not prove a collapse happened. What it proves is that a strong, shallow rupture just hit the exact crustal system a volcano was erupting through a few weeks ago. And that raises a question that no beach ball can answer. Can an earthquake that is purely tectonic still wake something volcanic? The honest answer is yes, and there are well-understood ways it can happen. This is not speculation pulled from nowhere. This is the physics that volcano scientists watch for every time a strong quake lands near an active system. So let me walk you through the machinery of it. Because once you see how it works, you will understand why nobody down there is relaxing just because the shaking stopped. Start with stress. A magnitude 6.4 earthquake does not just shake the ground and finish. It rearranges the stress field in the surrounding crust. Some places get squeezed harder. Some places get pulled apart. And in that rearrangement, fractures respond. New cracks can open. Old cracks can close. If you are standing on solid continental rock, that is an abstract idea. But around a volcano, those fractures are not abstract at all. They are the plumbing. That is the word to keep in mind. Plumbing. A submarine volcano is fed by a network of fractures and channels that let magma and superheated water move upward through the crust. It is a system of pipes carved into stressed rock. And here is why the earthquake matters. When you shift the stress in that rock, you can disturb the plumbing directly. You can clog a pathway that was open, and when you clog it, pressure starts to build up behind the blockage, like pinching a hose while the water is still running. Or you can do the reverse. You can crack open a pathway that was sealed and give pressurized fluid or magma a brand new route toward the surface. Either way, energy and pressure get redistributed underground. And if that is what happened here, we would not necessarily see the result today. We might see it over the next several days. That clogging scenario deserves a closer look, because it is the one that can turn a quiet volcano loud. When an earthquake seals or constricts the pathways that were letting gas and pressure bleed steadily out of a volcanic system, the pressure does not simply vanish. It keeps building behind the blockage, because the heat and the gas below do not stop. A system that had been venting gently, releasing its energy in a slow and manageable way, can become a sealed container with the burner still on underneath it. Given enough time and enough pressure, that container has to give somewhere. And when it does, the release can be far more sudden and forceful than the gentle venting it replaced. This is one of the ways a volcano that looked like it was calming down can surprise everyone. The earthquake would not have added any new magma. It would simply have changed how the existing system breathes, and a volcano that cannot breathe evenly is a volcano that can lurch. Whether anything like that happened beneath Titan Ridge is unknown, and may stay unknown until the sea offers a clue. But it is precisely the sort of hidden change that a strong, shallow quake in this exact spot is capable of setting in motion. That delay is one of the most important things to understand about this whole situation, so let me sit with it. When a strong quake disturbs a volcanic system, the response is usually not instant. It is not that the ground shakes and the volcano erupts in the same minute. The stress changes propagate. The fluids find their new paths. The pressure climbs. And then, days later, something shows up at the surface. This is why the story of the July 13th earthquake is not a story that resolved on July 13th. It is a story whose answer is still being written on the seafloor right now, in a language we can only read from orbit. It helps to know that this kind of triggering is not a fringe idea. Seismologists have documented again and again that large earthquakes can nudge other systems, sometimes far away. Strong quakes have set off small tremors in distant geothermal fields as their seismic waves rolled through, a phenomenon called dynamic triggering. Tides, which flex the crust ever so slightly twice a day, have been shown to modulate when certain faults and volcanic systems are most likely to move. These are small influences compared to the forces already stored in the rock, but they demonstrate the principle. A system sitting close to its tipping point can be pushed over by a relatively minor nudge, and a magnitude 6.4 rupture 85 kilometers away is a great deal more than a minor nudge. There is also the hydrothermal side of the plumbing to consider, not just the magma. A submarine volcano is wrapped in a network of superheated water circulating through cracks in the rock. Seawater that has seeped down, been heated by the magma below, and risen back up. That circulating water is under enormous pressure, and it is exquisitely sensitive to changes in the fractures it flows through. Shift those fractures with an earthquake, and you can change the temperature, the pressure, and the pathways of that hidden hot water system almost immediately, even if not a single new drop of magma moves. That is one more way the sea above could start showing signs of disturbance. And one more reason the coming days matter more than the day the ground actually shook. There is another mechanism, and it may be the most dangerous of all, because it does not require any new magma at all. It only requires shaking. Underwater volcanoes tend to accumulate a great deal of loose, unstable material. Fresh volcanic rock piled up during an eruption, ash and debris settled on unstable slopes, an edifice that may have been growing for weeks. Strong shaking can shake that loose, and on a hidden submarine structure, that possibility carries a weight far beyond the earthquake itself, because when a mass of material on a volcano's flank suddenly gives way underwater, it can move a volume of ocean that has nothing to do with how big the earthquake was. And this is where the central thread of tonight tightens into something with real stakes. A tectonic quake, shaking loose the flank of a hidden volcano, is not a story about the ground. It is a story about the water above the ground. So the real question stops being what the earthquake did to the rock and becomes what the rock might now do to the sea. Picture trying to inspect a building for damage after an earthquake, except the building is underwater. You have never seen its actual shape, and it is currently hidden beneath thousands of feet of ocean. That is the position scientists are in with Titan Ridge tonight. If this quake shook loose part of a growing volcanic structure down there, the ocean hides the evidence. We cannot look at the crater and check. There is no crater to look at. There is no modern high-resolution map of the ridge, and there was never any survey taken while it was actually erupting. This is a structure we found by watching the sea change color, and it is a structure whose condition, right now, we can only guess at. That blindness cuts both ways, and it is worth being honest about. It means we cannot confirm that anything bad has happened, but it also means we could not necessarily see it yet, even if it had. The first sign of trouble might not be immediate. The quake could have changed the fractures underneath the ridge, and the response could come later. So instead of watching the volcano, which we cannot do, scientists are watching for the sea to react, the same way it reacted when the eruption first began. Consider how thin our thread of observation really is, because it explains why every one of these signals carries so much weight. The satellites that spotted this eruption in the first place do not see the volcano. They see the surface of the sea in visible color and in infrared. When they detect discolored water, they are picking up the fine volcanic particles, dissolved minerals, and disturbed sediment that an eruption injects into the water, staining it green or brown against the dark blue. When they read a thermal anomaly, they are measuring the temperature of the sea surface and catching a patch that is warmer than it has any business being, and the underwater microphones fill in what light cannot reach, listening for the specific rumble and hiss of magma meeting water far below. That is the entire toolkit. Color, heat, and sound. No cameras on the crater, because there is no crater we can reach. That is also why the condition of the structure itself is such an open question. During the weeks it erupted, this volcano was building. Fresh volcanic material was being deposited on its flanks, piling up on slopes we have never surveyed, in a shape we have never confirmed. Newly built submarine volcanic material tends to be loose and poorly consolidated, the underwater equivalent of a steep pile of fresh gravel rather than solid bedrock. It has not had time to settle, compact, or harden. A slope like that is inherently unstable, and it does not take much to set it moving. So when a magnitude 6.4 rupture shakes a structure that spent 5 weeks stacking loose material onto unmapped slopes, the concern is not exotic. It is almost intuitive. You shook a fresh pile, underwater, in the dark, and now you are waiting to find out whether any of it slid. So let me tell you exactly what they are watching for, because this is the part where you get to follow along in real time over the coming days. There is a short list of signals, and each one means something specific. The first is the underwater sound. This region has hydroacoustic monitoring, instruments that listen to the ocean, and those signals had gone quiet for more than a month. If they rise again after July 13th, then something underwater has changed. That would be the earliest confirmation that the earthquake reached into the system. The second signal is steam. If a new puff of steam suddenly appears at the surface where the sea had gone calm, that becomes far more interesting and far more important than it would have been just a week ago. The third is heat. If the thermal anomalies return, those blooms of warmth in the infrared, that suggests fresh hot material has moved close to the surface again. And the fourth is the pumice. If pumice starts appearing in new areas, in places the earlier rafts never reached, then the seafloor is producing new material once more, and the quiet phase is over. Now compare that to the calm scenario, because I do not want to leave you thinking the alarming outcome is the only one. If the satellite imagery keeps showing only small patches of discolored water, and the underwater sound stays flat, then this earthquake may have passed straight through the system without reactivating anything. In that case, it was simply a strong tectonic quake in a very active zone, and Titan Ridge goes back to sleep. That's a completely real possibility. It may even be the most likely one. But here is the revelation that sits at the center of this entire investigation, and it is the reason the ocean surface matters more than any bulletin. On a hidden submarine structure like this one, the first warning of real danger is not going to come from a warning center. It is going to come from the volcano's own signals. Because the specific hazard that scientists quietly worry about here, a flank of the structure giving way and shoving a wall of water outward, is exactly the kind of event that our warning systems are not built to catch in time. Which means the eruption itself, the color in the water, the sound in the sea, is the warning. And that reframes everything about why a harmless earthquake is being watched so closely. So why can our tsunami systems catch the wave from a big earthquake, but not the wave from a collapsing volcano? To answer that, you have to understand how tsunami warnings actually work, and why this particular volcano sits in a blind spot. When a large undersea earthquake happens, warning centers can estimate the tsunami risk quickly, because there is a rough relationship between how the fault moved and how much water it displaced. That is how the Pacific Tsunami Warning Center was able to look at the magnitude 6.4 and say confidently and correctly, no tsunami threat from this earthquake. And I want to stress that they are almost certainly right about that. The earthquake, as an earthquake, did not move enough seafloor to raise a dangerous wave. But read that sentence carefully, because there is a gap hidden inside it. The all clear is an assessment of the earthquake. It is not an assessment of what the earthquake might have done to an unstable volcano nearby. Those are two completely different hazards, and only one of them fits neatly into the warning system. The wave from a fault, the system can estimate. The wave from a landslide, a chunk of a volcano's flank sliding into the sea, is a different animal entirely. It does not scale with the earthquake that triggered it. A relatively modest quake can knock loose a mass of material that displaces far more water than the quake itself ever could. And by the time that happens underwater, out of sight, there may be no time left to warn anyone. The physics of why a landslide wave is so hard to handle comes down to volume and speed. An earthquake generates a tsunami by shoving the whole column of water above the fault upward or downward in an instant across a broad area. Warning centers can model that because the fault motion and the displaced water are linked in a way they understand well. A landslide works differently. A mass of rock and sediment lets go and accelerates down a slope, plowing into the water and displacing it violently and locally. The size of the resulting wave depends on how much material moved, how fast, and how far it fell, not on the magnitude of whatever triggered it. That is the disconnect. A quake the warning system rates as harmless can dislodge a volume of material the warning system never accounted for, and the wave that follows arrives with no seismic fingerprint large enough to have raised an alarm in the first place. This is not a hypothetical fear invented for a video. This is a pattern this exact region has shown before, and we covered it in detail in our video from June 15th when we looked at the tsunami risk this volcano carries. I am not going to reteach all of it tonight, because if you have been following along, you already know the history. But the short version is this. This arc has produced landslide-driven waves in the past. Waves generated not by the shaking itself, but by masses of material collapsing into the sea. And the events that caused them were, in some cases, earthquakes that, on paper, looked almost too small to matter. The water did not care what the magnitude was. It cared how much material moved. So, layer that onto tonight. We have a magnitude 6.4, substantially stronger than anything in this year's earlier sequence. We have it breaking shallow, only 10 kilometers down, which is exactly where the stress transfers most efficiently into the upper crust near the seafloor. And we have it landing right beside a volcano that spent weeks piling up fresh, loose material before it went quiet. Each of those three ingredients, on its own, would be a footnote. A strong quake, far from anything, is a footnote. A shallow rupture in empty crust is a footnote. A pile of loose material sitting undisturbed is a footnote. The problem is that all three showed up in the same place at the same time, and that is a combination the historical record tells us to respect rather than dismiss. I am not telling you a wave is coming. There is no evidence of one, and the most likely outcome remains that nothing dramatic happens at all. Geography sharpens the stakes here in a way worth stating plainly. The communities of Manus Province, the very people who felt the earthquake as a light sway, and who earlier watched pumice choke their harbors, sit on islands scattered across this sea. A landslide-driven wave born at the volcano would not have to travel far to reach inhabited coastlines, and it would arrive fast. This is not a case where a wave would have hours to cross an open ocean while warnings raced ahead of it. In a confined sea near populated islands, the margin between the event and the impact could be measured in minutes. That is the uncomfortable core of why the honest answer to the tsunami question tonight is not a simple no. It is a no from the earthquake itself, paired with a careful eye on the one hazard the systems cannot promise to catch. Not panic. Attention. The difference between those two words is the difference between fear and preparedness. And preparedness is the only useful response to a danger you cannot yet see. What I am telling you is why scientists cannot simply file this away, and why the honest answer to the tsunami question is not a flat no. It is a not from the earthquake, and we are watching the volcano. That distinction between the hazard the system can see and the hazard it cannot is the real reason this story keeps me up at night a little. Because the operative warning, the thing that would actually tell us trouble is coming, is the same set of signals we have been talking about all along. The sound rising in the water, the steam, the heat, the color. On a structure this hidden, those are not just interesting readings. They are the alarm. And that brings us back to a question of timing, because this earthquake did not arrive at a random moment. It arrived right after the system had gone silent, and that sequence is stranger than it first appears. Let me put this earthquake back into its sequence, because on its own, a magnitude 6.4 is just a number, and the number does not tell you why the timing unsettles the people who study this. Earlier this year, as Titan Ridge erupted, the ground around it was busy. A magnitude 5.4 struck on May 15th. A magnitude 5.7 hit near the eruption site on May 22nd. And after that second one, the eruption changed. The activity weakened. The underwater signals declined. The whole system began sliding toward the quiet phase that would last more than a month. Look at the rhythm of that sequence for a moment, because it matters for reading tonight. The quakes during the eruption clustered in the magnitude 5 range, 5.4 in the middle of May, 5.7 a week later, with a swarm of smaller events beneath them that the instruments could barely resolve. They came while the volcano was visibly awake, and they tracked the eruption's own rise and fall. Then the pattern went quiet along with the eruption. For more than a month, nothing large registered. That silence is the baseline the July 13th event just broke, and it broke it not with another magnitude 5, but with a magnitude 6.4, a genuinely different class of event that released, as I mentioned earlier, an order of magnitude, more energy than anything the eruption itself produced. So notice what did not happen. This magnitude 6.4 did not strike during the peak of the eruption, when the plume was climbing toward 28,000 feet and the sea was staining green. If it had, we would fold it into the eruption and move on. One more quake among many while the volcano was obviously awake. Instead, it struck after the quiet had settled in. And that is precisely why it is more suspicious to a lot of people, and, I would argue, more scientifically interesting. You might think the opposite should be true. You might think a quake during a quiet phase is less concerning than one during an eruption. It is not that simple, and here is why. A volcano can look calm at the surface, while the seafloor around it is still adjusting. The eruption dropping below our detection threshold does not mean the crust suddenly became stable and cooperative. That same fault system is still there. That same magma-heated environment is still there. None of it went away just because the surface went quiet. So a strong quake arriving now is not landing on a dead system. It is landing on a system that only looks dead from above. And that is the whole reason we keep returning to the central thread tonight, that the calm on the surface is not the same as calm underneath. There is a larger precedent worth mentioning here, briefly, because it shows this concern is grounded in more than one volcano. When a very large megathrust earthquake struck off Kamchatka in the Russian Far East, the broader region afterward saw submarine and near-shore volcanic activity stir. I want to be careful with that comparison, because it is directional, not deterministic. It does not mean a big quake always wakes a volcano. It means that major shallow ruptures near volcanic systems have, in the real record, sometimes been followed by changes in those systems. It is a reason to watch, not a reason to predict. And watching on a hidden structure we can barely map means watching the ocean surface. It is also fair to weigh how often this kind of concern resolves into nothing, because intellectual honesty cuts both ways. Strong earthquakes strike active volcanic regions around the world regularly, and the overwhelming majority of the time, the nearby volcanoes do not respond at all. Most quakes near most volcanoes are simply quakes. If you played the odds blindly, you would bet that Titan Ridge sleeps through this one, and you would usually be right. But odds are built for situations you can see, and this is a situation we largely cannot. The reason this particular pairing earns closer attention than the raw statistics might suggest is the pileup of specific factors: a shallow rupture, a strong magnitude, a location right on the volcanic junction, and a structure freshly built and freshly quieted. None of those factors guarantees a response. Together, they are enough to justify watching the sea instead of shrugging and moving on. So the timing gives us the shape of the question. A stronger quake than any that came during the eruption, arriving after the eruption went quiet, into a crust that is only pretending to be still. If nothing changes in the days ahead, it was a powerful tectonic event in an unforgiving zone, and that is that. But if even one of those old signals returns, the story does not just continue. It reopens for the volcano and for the wave. And it turns out this is not the only hidden system on Earth, twitching in a way that has scientists leaning closer to their screens. Halfway around the world from the Bismarck Sea, near Naples, there is another restless system being watched with the same unease. A caldera with something like 6 million people living on and around it, where unusual measurements at a crater called Solfatara have been quietly climbing. I mention it not to change the subject, but because it makes the same point Titan Ridge makes. The Earth has these hidden pressure systems, some under cities, some under open ocean, and they do not announce themselves on a schedule. They shift, and we scramble to read the signs. If you want to see what that looks like when the system is right underneath millions of people, that is its own story worth your time. But tonight, our system is the one under the sea. So what does the waiting actually look like in practical terms? It looks like scientists pulling each new satellite pass as it comes down and comparing it, frame by frame, against the images from before the earthquake. It looks like watching the traces from the underwater microphones for any rise above the flat line they have held for over a month. It looks like checking whether the small residual patches of discolored water are shrinking, as they should if the system is truly winding down, or whether they are brightening and spreading, which they should not. None of this produces an instant answer, and that is the hard part to accept. There is no single moment where an official steps up and declares the volcano safe or awake. There is only the accumulation of the next image, and the next, and the one after that, slowly building a picture of whether the earthquake changed anything down there or passed through the system like a wave through an empty room. So let me bring this all the way back to where we started, and be honest about what we know and what we are still waiting to learn. We know a magnitude 6.4 earthquake struck the Bismarck Sea on July 13th. We know it was shallow, about 10 kilometers down. We know it was tectonic. The beach ball told us that. Oblique strike slip with a normal component. The crust breaking under its own twisting stress. We know it did not, by itself, raise a tsunami. And we know it caused no damage on land. And we know it landed about 85 kilometers from a volcano we cannot see that erupted for weeks this year, and that had only just gone quiet. What we do not know is the one thing that matters most. We do not know whether that earthquake reached into the volcano's plumbing and disturbed it. We cannot know it yet because the answer is being written underwater, in a place we can only observe from orbit. So, we wait for the sea to tell us. If the coming satellite passes show only faint patches of discolored water, and the underwater microphones stay silent, then the crust took the blow, and the volcano slept through it. That is the good ending. It is a genuine possibility, and it may well be the one we get. But if the sound in the water rises again, if a new column of steam appears where the surface had gone flat, if the heat signatures bloom back into the infrared, if fresh pumice starts drifting into waters it never reached before, then something underneath Titan Ridge has changed, and this quiet, harmless, no-damage earthquake will turn out to have been the push that woke it. The whole story sits balanced on the next set of images, on data that has not come in yet as I speak to you. That's the part I find genuinely difficult to sit with. We are used to danger that announces itself. A quake you feel. A siren that sounds. A wave you can see coming. But the hazard here is the opposite kind. It is silent, it is hidden. And its first sign, if it comes at all, will be so subtle that only a satellite watching the color of the sea will catch it. An earthquake struck something massive under the Pacific, and whether that matters or not is not something a scientist can declare today. It is something the ocean will decide, on its own timeline, in the days ahead. So here is the question I will leave you holding until the next images come down. When the answer finally arrives, will it reach us as a faint green stain spreading across a satellite photo? Or will it reach the islands first, as a wave?